This video is going to deal with big O notation, which is something that computer science students will almost certainly have seen before. You might be surprised to learn that it's useful in number theory also. So in the computer science context, it's used to express the efficiency of algorithms and the computational complexity associated with solving a problem in a certain way. So you know, something like searching through a list, or sorting a list into ascending order, or alphabetical order, or some other criteria. There are various algorithms that will do this. Some of them are slower, some of them are faster, and we can compare them and classify them based on their efficiency and the complexity, and also how the time to complete the computation varies as we vary the size of the input data set. So if we give it a set of 100 data points, it might complete it in a certain amount of time, but if we double the input size, would it double the length of time that it takes, or would it change it exponentially, quadratically, and so on? So we can answer these questions and analyse them using big O notation. And in number theory, it's not really the complexity or the computation time of algorithms we're interested in, but we're interested in functions in the way that we would be in analysis. You know, we're interested in their asymptotic behaviours, limits, what behaviour they exhibit as we approach limiting values. So big O notation is a way of formalising this, and in number theory it's very practical to use big O notation because it allows us to not keep track of constants that might otherwise confuse the picture. So we're going to define some new notation, obviously here. So we're going to define big O, we're going to define little o, and we're going to define the asymptotic sign. And we'll also look at some related notations, such as these curly inequality things and this sort of curly equality sign, for lack of a better word. These symbols are related to these symbols, but first of all let's define the first three here. So in order to get started, we just need some definitions to get going. So we're going to say that x, say let x be a continuous variable, and we're going to say that x takes some limiting value, or x, we're going to look at situations where x tends towards infinity or 0 or some other limiting value. So we're going to define phi of x to be some arbitrary function, some arbitrary positive function. So it's a non-negative valued function of x, and we're going to say that f of x is just any other arbitrary function of x, positive or negative. So with this, we can get started. So the first thing we want to define is big O. So if we've got these functions phi and f, we can say that f is big O of phi, and that's the way that we would read such a statement. F is big O of phi. Now what does that mean? It means that the absolute value of the function f is always bounded by the function phi multiplied by some constant a. So a is just some multiplicative constant, which we can find such a constant where if we multiply it by phi, the resultant function will always give a bound on the absolute value of f. So let's illustrate this with an example. So in hard team right, we use 10x is big O of x. Now, the reason this is true is that the absolute value, so 10x is a linear function of x. The rate of change is constant as x increases, 10x increases 10 times as quickly. But the absolute value of the function 10x, it can be bounded by a times, in this case our phi is simply the function x itself. We're not doing anything to the input to get phi. In other words, phi maps x to x. If we can find some constant a which gives us a function which always bounds the absolute value of 10x, then we can see that 10x it must be big O of x. So a could be any number greater than 10. So 11 x would be a function which would strictly bound the absolute value of 10x, and any other number greater than that would also work. So we can see, as long as we can find at least one number a which meets this requirement, then we can say that the function f is big O of the function phi. In this case, 10x is big O of x. And just to give one quick other example, we can say that sine x, and also these are, in these examples we're going to assume that x tends to infinity, so we're interested in the behaviour of the functions as x goes to infinity. So sine of x is big O of 1, because obviously sine of x oscillates between -1 and 1 and all values in between, so it never exceeds the absolute value of sine x is always strictly less than or equal to 1, and if we multiply 1 by some constant a, we just get a. So as long as a is greater than 1, then that function, so keep the little 1 in here just so that you can see rather than suppressing it. As long as a is greater than 1, when we multiply it by the function, which is just always valued at 1, we'll have a bound where, so if this was anything, if this was 2, say, then the absolute value of sine of x will never exceed that bound, so it will strictly be within those bounds, and therefore sine of x is big O of 1. Okay, so that's big O. Little o can be defined by, so if we said that f is little o of phi, that would mean that the ratio f to phi tends towards 0 as x approaches infinity. So we're using this implication arrow, which we defined previously, now in a different way. It's no longer an implies arrow, it's a tends to arrow, so the ratio of these functions tends towards the value 0, so this is more of an analysis notation. So hopefully the context will keep anyone from getting confused between logical implication and analysis limits. Finally, we want to define the asymptotic sign. So if we say that f is asymptotic to phi, then that just means that the ratio f to phi tends towards the value 1. So these three notations are very useful in number theory and in computer science. We can refer to them all under the umbrella term of big O notation, and they also get called asymptotic notation because we're looking at asymptotic behaviour of functions, and we're interested in limits and so on. So let's quickly define the three other symbols that I mentioned, and then we'll move on. If we say that f is curly less than phi, that means that f over phi tends to 0. So that's essentially the same as saying it's little o of phi. Not much utility in that one. If we have the curly greater than symbol, that means that f over phi tends to infinity. And lastly, if we say that f is curly equal to phi, that tells us that a phi is a bound on f. Now these two a's are different multiplicative constants that we can find such that f will strictly be bounded by these two phi functions with their respective multiplicative constants. And this last symbol can be read f is of the same order as phi. So that's probably the best way to say it. So we'll just look at a few final examples to illustrate the notation that we've introduced. So if we had two functions of x, f of x could be equal to x, and say g of x equal to x squared. And we're interested in the behaviour as x tends to infinity. So we're going to seek some kind of relationship between f and g. So we want to say that f is something of g. So f could be little o of g or big O of g, or they could be asymptotic to one another maybe. But we'll need to investigate further to determine what the relationship between these two given functions is. So we can start by taking the ratio of f to g, which here would be x over x squared, which equivalently is 1 over x. And since we're interested in the limit as x tends to infinity, as x gets bigger and bigger, 1 over x tends to 0. And remember the condition that if the ratio f over g tends to 0 for the asymptote that we're interested in, then f is little o of g. And little o of g is a stronger statement than big O of g, which is necessarily implied by little o of g. So if we know that f is little o of g, then we know that f is also big O of g. It has to be because if the ratio tends to 0, then we must be able to find the multiplicative constant such that f, well, the absolute value of f is bounded by that constant times g. That's a weaker statement. Okay, so what now if we choose a different limit for x? If we say that x is tending to 0, what would be the relationship between the two functions then? Well, in this case, we could take the ratio g over f, which would be x squared over x, which is just equivalent to x, and as x goes to 0, so we can see that g is little o of f in this case, and equivalently g would be big O of f. So we can write out so that this f going back to the previous one, f equals little o of g. That's the same as saying that x equals little o of x squared. Similarly, x squared is little o of x, and again, because we've shown that a function is little o of another function, then we must also conclude that x squared is big O of x. But again, these conclusions only hold when x is tending towards 0. These conclusions here, so I can just write this out explicitly. X is big O of x squared. These conclusions hold when x tends to infinity. So I hope that helped illustrate the idea of big O notation and little O notation. It takes a little time to get used to, perhaps, but if you're a computer science student, you might recognise some of this stuff already.